Imagine your everyday gadgets running faster, wasting less energy, and costing far less to make. That's the promise of a tiny chip we built for our final year project. I'm Junaid Khalid, and my teammate Ahsan Abbas Kazmi. Welcome you all. Together, under the guidance of engineer Muhammad Ali and co-supervisor Professor Dr. Nadia Nawaz Qadri, we designed something special. Modern devices perform millions of multiply and accumulate operations every second in AI cameras, fitness trackers, even your microwave's touch panel. But generic processors burn unnecessary power doing that heavy lifting. So we asked, why not add a dedicated accelerator that speaks the open source RISC-V language and does Mac operations smarter? Meet our multi-mode Mac unit, a tiny accelerator that plugs into a RISC-V core like a turbocharger. Multi-mode means it can switch between 2-bit, 4-bit, 8-bit, and 16-bit arithmetic on the fly. Big jobs? Small jobs? It adapts. Here's why our solution stands out in the market. Unmatched speed. Our Mac unit crushes complex calculations, enabling real-time AI, video processing, or 5G applications. Ultimate flexibility. With multiple modes, it adapts to any device, from low-power IoT sensors to high-end servers. One chip, endless possibilities. Power savings. It slashes energy use by offloading heavy tasks, meaning longer battery life for wearables, drones, or edge devices. Save power, save costs. Cost-effective scalability. Built on open-source RISC-V, it's affordable to customize and deploy, cutting development costs for startups and giants alike. We designed this to solve real-world problems. Whether it's a smart home device learning user habits, a self-driving car navigating in real time, or a data center optimizing AI workloads, our solution delivers faster performance, lower costs, and sustainable innovation. What's next for our project? The possibilities are huge. Powering AI at the edge for devices like cameras or robots, boosting IoT with low-power, high-speed computing, supporting next-gen networks like 5G and beyond, growing the RISC-V community to spark global innovation. We developed a multi-mode Mac unit supporting 2x2, 4x4, 8x8, and 16x16 multiplies at runtime. It offers fast reads and writes over an AXI4 full interface and integrates via an AXI crossbar into the SweRV EH1 core on a Xilinx RISC-V FPGA. At the heart is our parameterizable Mac data path. One logic block handles all 4 precision modes. An internal accumulator sums products across vector inputs with stride, padding, and length configured by firmware, giving flexibility without extra logic. Let's walk through the multi-mode Mac data path step by step. At the top left, we have two 16-bit input operands, A and B, carrying our data. A small control unit, mode selection, tells the hardware which precision to use. Down the right side, you see 4 dedicated multiplier blocks. A 2x2 multiplier that consumes only the bottom 2 bits of A and B, a 4x4 multiplier using bits 4 bits, an 8x8 multiplier using bits 8 bits, and a full 16x16 multiplier. Each block produces a 32-bit partial product and asserts a select code that identifies its output. All 4 32-bit outputs feed into a single 4-to-1 multiplexer. The mode code drives that multiplexer, so when mode is 00, you get the 2x2 result. When it's 01, you get 4x4, 10 gives 8x8, and 11 gives 16x16. The multiplexer's output is the product. Below, we accumulate these products. Product and the current accumulator out feed into an RTL adder, which sums them arithmetically. Its 32-bit sum goes into the accumulator out register, a clocked register with 2 control signals. Clear, which resets the accumulator to 0, and accumulate_enable, which latches in the new sum only when asserted. Data flows from the CPU through the crossbar to the Mac, then back to memory, all under burst control for high throughput. On RISC-V, our full system on chips plus Mac uses only 216 LUTs and 64 registers, just 0.34% and 0.05% of the device. Compared to Pulpino's fixed 4x4 unit, we achieve 24 times fewer LUTs and 8 times fewer registers, yet support multiple precisions, interrupts, and AXI bursting. Our design meets timing with positive WNS, meaning the longest data path fits within 150 MHz clock cycle, providing plenty of margin for reliable operation. On the Galaxy's board, a 150-byte transfer at 18 kb/s takes around 8.14 milliseconds, well within acceptable latency for typical convolution workloads. Let's dive in and explore the RTL diagram of the complete system on chip. examining the SweRV EH1 core, the AXI interconnect, and the integrated MAC unit. Now let's dive into the emulation diagram and see how the SweRV EH1 core, the AXI interconnect, and the integrated MAC unit operate together in a virtual environment. We have run our comprehensive test benches, covering 2x2, 4x4, 8x8, and 16x16 multiplier modes, along with accumulator verification and burst mode scenarios, to validate every configuration.